and people will probably join late, which I understand because I was late. I'm going to go ahead and start. So I'm going over worksheet 21. I posted it last Thursday, I think, so it's been around. This is a little bit of just reviewing what we already did on the last worksheet, but practice with this stuff is best. It's the best way to learn. Okay, so it's kind of obvious for the most part, like if you can identify the nucleophile, what the product is going to look like, but stereochemistry is important, and that kind of depends on the mechanism we're doing. So for this reaction here, can anybody tell me if it's going to be SN1 or SN2? Yep, and the reasoning for it being SN1 is, well, the first thing, like I said last week, you should look at the substrate. If it's primary, it's going to be SN2, and if it's tertiary, it's going to be SN1. But the substrate with the leaving group, this is an allylic position. Thank you. This is an allylic position on top of being secondary. And allylic is good for SN1 because I can go ahead and show the mechanism, I suppose. So first, the oxygen takes a proton. I'm just going to show this so you can see why it's good. So you get water, and water kind of just leaves. And you get a carbocation. If he hasn't covered this, he probably will, but just like with radicals being more stable when they're allylic, carbocations are more stable when they're allylic because there's a resonance form like this with the double bond going towards the positive charge. And resonance makes things stable, so that makes the carbocation stable, which makes this basically when a leaving group is allylic, it's good for SN1. I think that trend also holds for SN2 though, so I mean I might be wrong about that, but I know for a fact this cation stability is a thing. So basically the substrate doesn't tell us if it's going to be SN1 or SN2, but the nucleophile and the solvent are good indicators. So this nucleophile here, we have hydrochloric acid. Is that, well, is it a strong or weak nucleophile, I guess? Can anybody tell me that? I guess I'll finish the mechanism since I've pointed out. Chlorine just attacks. Okay. It seems like the answer is no. So okay. So a strong nucleophile is generally something with a negative charge, like a hydroxide or something similar, because it has a negative charge. It wants to get rid of the negative charge by giving it away to something. The hydrochloric acid is an acid, it's not a base, and bases are usually good nucleophiles, so because it's an acid, it's not a good nucleophile. It's a relatively weak nucleophile. And SN2, I mean SN1 generally favors acids or weaker nucleophiles. Sorry, I know it's getting a little cramped, but this is the nucleophile SN1 tends to favor. which is what hydrochloric acid is. And also this solvent here, can anybody tell me if it's polar protic or polar aprotic? It's protic, yeah. So SN1 favors protic solvents, which this is. ETOH is ethanol. And in order for something to be protic, you have to have a hydrogen attached to oxygen, nitrogen, or sulfur, I think it was on his slides. So like here, that's what the solvent is. This is just ethanol, and there's a hydrogen attached to an oxygen. And what makes it protic is this can do hydrogen bonding and stuff with other things. And this has a sort of stabilizing effect for SN1 mechanisms that you don't have to worry too much about, that you should just know that a protic solvent is good for SN1. So the nucleophile is an acid, which is good for SN1. The solvent is protic, which is good for SN1. So this does an SN1 mechanism. And what happens to stereochemistry when you do an SN1 mechanism? I've kind of already shown it, but can anybody say or point it out? So we started with this being a chiral center here, and the stereochemistry was shown. I didn't show the stereochemistry in the product. I did that on purpose. Yeah, I guess that's the way you could put it. So this is something I covered in the last workshop. It goes through a carbocation intermediate, and a carbocation is sp2 hybridized. It's trigonal planar for the geometry. So you have like, there's some random stuff bonded in the flat trigonal planar area, and then there's the empty p orbital. So the chlorine could either attack from the top or the bottom. It doesn't really care. It's going to attack both roughly equally, so you're going to get like an equal mixture of the two enantiomers, and that means you can basically say that it loses its chirality because it forms a racemic mixture. That's just a really long way of saying you lose chirality in an SN1 reaction because of the carbocation intermediate. If you just want to remember that small sentence I just said, that's fine. If you pass through a carbocation, you're not going to have stereochemistry in the product. Okay. Does anybody know what the mechanism for this one is going to be? SN2, yes. And the reasoning for that, first you look at the substrate, that's the most important factor. This carbon with the leaving group is only bonded to one other thing, so it's primary. So, well, it's also allylic, so it could potentially be SN1 because it's right next to the double bond. So that's important to factor. Like a primary allylic cation is roughly as stable as a secondary cation, I think. So it would still have the potential to be SN1. But then we look at the nucleophile, and is the nucleophile here a strong or weak nucleophile? Strong, yeah. And we know that because sodium, like we don't see a negative charge like I was pointing out for the hydroxide, but sodium is just a counter ion, so it has a +1 charge. It's sort of stabilizing the negative charge on the sulfoxide here, the sulfur. So there's a negative charge. It's a strong nucleophile. It wants to get rid of the negative charge. And that is what SN2 reactions prefer. They prefer strong nucleophiles, which are strong bases or pseudoneutral. Okay, and DMF, is that polar protic or polar aprotic? It's aprotic, yes. I can draw the structure, or you can just Google it, but the way I remembered it when I was taking the class is if you see an acronym that looks, if you see an acronym, it's more than likely aprotic. Most of the protic solvents are either water or alcohols, and they don't really have acronyms. And then there's acetonitrile, which is also aprotic. But if you can recognize it, then you should know by its structure that it's aprotic. I guess since I brought it up. This is acetonitrile. There's no hydrogens on any polar things like the nitrogen, so it's aprotic. So the nucleophile is the SCH3. That's what substitutes for chlorine. And there's no chirality because there's two hydrogens here, so I don't show a dash or a wedge for the product. Okay, like always, feel free to, oh, that wasn't number 2, but feel free to stop me if questions, if I do something that's confusing. Okay, so I don't think he's going to use this as an example or like a question on a test because this is just kind of abstract, at least at this level. But I'm going to go ahead and go over it. So the nucleophile here is this. It's a carboxylic acid, but with the proton gone, so there's a negative charge on one of the oxygens. Hopefully, well, you guys didn't have to memorize the pKs, but carboxylic acids are relatively strong acids. And do you remember, like, if one acid is stronger than another, like, what can we say about the conjugate base? Like, because this came from a strong acid, is this a strong or weak base? It's a weak base, yeah. And we can justify that with the resonance form. Resonance makes things stable. The more stable they are, the less reactive they are. So the less reactive the base is, the weaker the base is. So this is a weak base, which also means it's a weak nucleophile. And that favors what kind of reaction? SN1 or SN2? Yep. And on top of that, our solvent is a protonated form. It's acetic acid. Is that aprotic or protic? Yep, it has, there's an oxygen here. That's not what it looks like, but yeah, I don't think you'd ask this, but if you understand my explanation of this, I think most other questions won't be too bad. If you don't understand, please ask me to explain more, but, oh, what the hell? Sorry. But, yeah, so this is a weak base because of the resonance, which means it's weak nucleophile, which means it's good for SN1. The solvent is protic because there's a hydrogen on the oxygen. So it's polar protic, which is also good for SN1. And we couldn't tell based on the substrate because it's secondary and allylic, but now we know that it's SN1 because of everything I just covered. And because it's SN1, we're going to lose the chirality or the stereochemistry. It's still a chiral center. We just don't know the stereochemistry anymore. And the oxygen here with the negative charge is what's going to attach. So it's going to look a little funky. But that's a way of kind of condensing it. It actually looks like didn't actually draw this, but it'll look something like this. And this is actually an ester, so I think this is actually a reaction you're going to go over next semester, but you've seen it here in the context of SN1 and SN2, so yeah. Everything else is relatively simple compared to that. Okay, so what will this be, SN1 or SN2? SN2, yes. First, you look at the substrate. It's primary, so, and there's no double bond here, making it allylic, so it's pretty much only going to be SN2 regardless of conditions. Never mind, I'll ask. So in addition to that, you have potassium as a counterion and cyanide, which this is a strong nucleophile. It's not a strong base, but it's a strong nucleophile. So that's good for SN2. This is not polar protic or polar aprotic. It's basically non-polar, I guess is how I'd classify it. It's probably a little polar, but it's not protic or aprotic. It doesn't fall into either category. So it doesn't really slow down or speed up the reaction. It's kind of just there. So this could be good for either SN1 or SN2. So if you have THF or ether, then that doesn't mean much. And you have to look at the nucleophile and substrate. But like we already said, based on the substrate, it's SN2. And this is the product. Because the C has the negative charge, it just attacks there and kicks out the iodide. What mechanism will this go through? Yep. And again, we can figure it out based on the substrate. It's tertiary, which is good for SN1, terrible for SN2. This is also an acid for the nucleophile, so it's a weak nucleophile. Again, the ether solvent doesn't really influence either way, but the substrate and nucleophile are good for SN1. So that's your product. If this is seeming repetitive to you, that's probably a good sign. Oh, I guess I brought this back for another. No, never mind, that's not the same. Okay, is this going to be SN1 or SN2? Um, can you explain why you think it's SN2? So substrate is the first thing we look at, right? It's secondary. So we can't tell if it's SN1 or SN2 just based on that. What about this nucleophile? Do we have a negative charge on it that makes it a strong nucleophile and a strong base? No, this is ethanol. It's ethanol can act as an acid or a base, so I guess that's a bit of a weird thing. But yeah, the the lone pairs on the oxygen are what make it a nucleophile. And like I was saying, like the alcohols can be acids or bases, so I guess it's a little frustrating that because it can act as both, it's not really going to be a strong nucleophile, so it's going to be relatively weak. So I'll just put weak nucleophile. And it didn't put anything on the bottom of the arrow for the solvent, but I could have put this, like, that would have been kind of redundant because it's the same thing. Because ethanol is a common solvent and it can also act. Why is it a weak nucleophile again? Um, Alcohols can act as acids or bases. It's if it was deprotonated, it would be a strong nucleophile because it would have a negative charge. But in its protonated form, which is what we have here, it's not negative, so it's not a relatively strong nucleophile. It's, I mean, it's stronger than like a carbon with a hydrogen, I suppose, but it's not that strong, so it's relatively weak. Generally, like in terms of looking for strong nucleophiles for SN2, you're just looking for negative charges on things usually. So like the CN minus, the OH minus, or like you could have some carbon chain and then an oxygen at the end with a negative charge. So like if I did this, then it would be a strong nucleophile because the proton's gone and you have a negative charge. And it doesn't want to stay negative. That's why it is a strong nucleophile. It's very reactive. But if there's no negative charge, it's, I'd say, like 99% of the time, it's going to be a relatively weak nucleophile. So it would be better for SN1. So if you don't see a negative charge and you don't see sodium or potassium as counter ions, then it's probably a weak nucleophile. If I had to summarize what you're looking for, does that help, Jared? Okay, so yeah, no counter ion here, and it's not negative, so it's a weak nucleophile. So on top of being the nucleophile, like I was saying, it could, like it is also the solvent, but I didn't put this down here because it's kind of redundant. If you don't see anything on the bottom, you can assume the nucleophile is acting as the solvent. And we already discussed in the first parts, this is ethanol, and ethanol is a polar protic solvent, which is good for SN1. So weak nucleophile and protic solvent are both pointing towards this being an SN1 reaction. So because it's SN1, I'll just do this. That's standing for ethyl. It's just the two carbons there. It's because it's SN1, there's no stereochemistry in the product. because of the carbocation intermediate. Okay. What kind of mechanism will this be? So substrate is the first thing we should always look at. It's primary. So straight off the bat, that's kind of indicating that this is going to be SN2. And in addition to the substrate being good for SN2, we have a negatively charged nucleophile. So that's a strong nucleophile. And then E for solvent doesn't really go one way or the other, but the substrate and nucleophile both point towards this being SN2. So this is that reaction you guys learned right before your last exam. It's just an acetylide ion reacting with an alkyl halide to form a carbon-carbon bond. So we basically just put this carbon here where this chlorine was. And then there's the triple bond and one extra carbon, so we added 3 carbons. I'm just pointing it out because it's good to count your carbons to make sure you didn't add the wrong amount. That's not really the focus of a question like this, but it would probably be important for like partial points. Something. Okay. So what mechanism do you think this would do? It looks like it, doesn't it? Yep, it's a tertiary position. So it's a tertiary position, so that favors SN1, but we have NaCN, and what kind of nucleophile is this, strong or weak? And then the solvent is protic or aprotic. It's DMSO. It's one of the weird abbreviations, so it's aprotic. Yeah. Like I was saying, anything that has like a weird acronym or abbreviation, like DMSO or DMF or HMPA, like all of those are aprotic. So both of these are pointing towards it being SN2, but it's tertiary, which kind of disfavors SN2. So I put in number 1 if no reaction would occur, right? NR. So it looks like this would be NR because both the nucleophile and the. Did you guys learn about elimination reactions yet? No? Okay, well, this is actually a case where wait. Yeah, I think it would do an E1 reaction. But because you haven't learned that yet, you wouldn't know that. So that's why it's NR in this context. By the time you get to your test, you'll have learned what the mechanism would have been there, but don't worry about it for now. So how far did you guys get on the lecture today then? Did you finish SN1 discussions? Okay. So I guess I'll start asking elimination questions on the next worksheet then. Okay, that's good to know. All right, so what kind of mechanism is this going to be? SN1 or SN2? Yeah, so first thing we look at substrate, as always. It's secondary, doesn't tell us one way or the other. So we turn to the nucleophile. We have a negative charge on the bromine and a positive charge on the sodium. So negative charge means relatively strong. This isn't the best nucleophile, but it's negative, so it's relatively strong. And is this protic or aprotic, the solvent here? Yep, it's aprotic. This is acetonitrile. It's one of the more common aprotic solvents that doesn't have one of the abbreviations I was talking about. But even though it doesn't have an abbreviation, you should recognize that there's a nitrogen here, but no hydrogen on it, so it's aprotic. So this is going to be an SN2 reaction. We know that the bromine is the nucleophile because that's what has the negative charge. So that's what's going to replace the OTOS here. What's going to happen to the stereochemistry? Because it's an SN2, yeah, it's going to invert, reverse. So we started with a wedge and the stereochemistry is going to become a dash. Yeah, you got it. So SN1 leads to a loss. I'll go ahead and write it. Lose stereochemistry. And SN2 inverts it. And if you're not shown stereochemistry, then you don't really have to worry about these, like some of the problems, or if I had just given you this, I didn't show if it's a dash or a wedge, and you don't know what it started as, so you wouldn't know what it inverts to, so you would just draw that as a line as well. But if you are given dashes and wedges, you have to worry about these characteristics. Okay. Number 2. Does anybody have an idea of how this can happen? It's definitely not what you would expect if you were doing this, but that is not exactly. So I believe you're thinking of like this reaction where we would add like a radical here and then it would react with a bromine at the allylic position, but we don't have a double bond here. And we're not using radicals, we're just using HBr and THF. Water does form, yes, so that is a byproduct. Yeah, the reaction mechanism is SN1. That's a really good thing to identify. Oh, the BR breaks off. Yeah, yeah, that's what's gonna happen. It acts as the nucleophile. Okay, so yeah, that's the first step in the SN1 here. So like, it takes the proton from the bromine. We have a positive charge on the oxygen, and I'm assuming the cation intermediate you're talking about is when the water leaves. This is as far as I see in your explanation, but how do we get from here with the cation here? Like, normally the bromine would just attack this, and we wouldn't get that product we have up there, right? But yes, that is what I was looking for. There's a hydrogen here. It can take the hydrogen and the electrons and push it towards the positive charge. Now there's a lack of electrons here on the tertiary position, so we went from a secondary to a tertiary cation. We formed a more stable one, so this can happen, and it probably will happen to some extent. And then the bromine attacks, and you get that. If you didn't even mention this in lecture, like at all, I wouldn't worry about it too much, but this is something that I was expected to know when I took the class. That's why I'm bringing it up. So if you're doing an SN1 reaction, you know that it's passing through a cation intermediate. That's one of the defining characteristics. And from the past, you learned that cations can do hydride and alkyl shifts. So just try to keep that in mind if he asks a question somewhat related to like, how do we get a product like this from something like this, where like it changes positions. It's more than likely a hydride shift or something similar. So hopefully that makes sense to everybody. And hopefully this demonstrates that all the stuff you guys learned in the past few months is kind of coming back, like it all connects together after a while. Right, what's wrong with this reaction? What do these conditions, yeah, it shouldn't be SN2, it should be SN1. And why? Yeah, this is a weak nucleophile, and ethanol is also the solvent, and ethanol is a protic solvent. So weak nucleophile, protic solvent, those are all SN1 conditions, which means that we wouldn't invert the stereochemistry, which is what we're seeing here with it going from a dash to a wedge. So that is, actually looks a bit like it too. That's what's wrong with this. These are SN1 conditions, but we drew the product as if it was SN2. So to fix it, if we wanted to fix the conditions, what nucleophile could we use to get that same product? So if we used sodium hydroxide, that would just lead to this. So that's pretty close. because that does use an oxygen, but it's not exactly what we're looking for. We still want the oxygen with the ethyl group on it. So instead of sodium hydroxide, we do want this counter ion, but I can write it like this, NaOET, and that is just this, because the ET stands for ethyl. This is an ethyl group, and then the negative oxygen. Does that make sense? Just counter ion, and then the ethyl group, and we get that. And now because there's the negative charge here, this is a strong nucleophile, so it's like ethanol and F oxide are like they're going to lead to the same general product, but one is a strong nucleophile while the other is weak, so it might do a different mechanism. Okay, so this is a strong nucleophile, and solvent doesn't really matter, but we could use any aprotic solvent just to try to be consistent. Could be literally anything, DMF, DMSO, acetonitrile, acetone. There's a lot of options, but these are some of the better ones. Or if we just wanted to take these conditions and like correct the product, there. Now if we're not showing the stereochemistry inverting, it's just it lost its stereochemistry. So that would be correct. You just fixed the product. I feel like a question like this is kind of common. I had one on most of my exams, like what's wrong with this reaction? Fix it. So hopefully this makes sense why it being SN1 and the product inverting stereochemistry was bad. Space. What's wrong with this reaction? This one's a little harder to spot, in my opinion. What kind of reaction or mechanism do these conditions favor, SN1 or SN2? Well, if you don't know, it is good to know. So SOCl2 with pyridine, and that's reacting with an alcohol. Those are SN2 conditions. And soda substrate at first glance looks like it's good for SN2 because the leaving group is on a secondary carbon. It's bonded to two other carbons. But if we SOCl2 is a bit different. Like there's an extra step in the mechanism. It basically, I should be able to, I think SOCl, let me look it up. I don't want to draw it incorrectly. I know I can show you the mechanism really quickly. I just need to know what that looks like. So basically what happens is At least I think, like I might have the arrow pointing in the wrong direction, but I know like the oxygen attaches to the sulfur here and one of the chlorines leaves. And then that's not where that goes. So alcohols by themselves are very bad leaving groups. And they're bad leaving groups because when they leave, you form hydroxide. Hydroxide's a strong base. It's very reactive, so it would probably just want to go back to where it came from. So it wouldn't stay gone. It wouldn't leave forever. It would come back. But when you use SOCl2 and it does this first step to convert the alcohol, probably has a positive charge too, and that makes it a better leaving group. And then the chlorine comes and does a backside attack. So this mechanism might not be perfect. I honestly just looked up the structure of SOCl2 and tried to do it on the spot, so there might be a mistake here. It's probably in the lecture notes somewhere, but it's something along these lines. And the point is, it's an SN2 mechanism because when the alcohol that's transformed leaves, the chlorine attacks from the back, which is SN2. Hopefully this looks somewhat familiar. That wasn't the point of this question, but it's good to understand why this is SN2. So I hope that cleared that up. I'm gonna make space though. This will be in a video if you want to look back at this later. I'm sorry if you were trying to copy it down. Just trying to save time. So at first glance, like I was saying, this looks like it would be good for an SN2 mechanism because it's on a secondary carbon. But if we look one carbon over here, this carbon is bonded to 4 carbons. It's quaternary. Do you guys remember last week when I talked, or also your professor talked about substrates that are next to a very bulky position, a quaternary position? What does that do to SN2 reactions? Yeah, it'll slow down to the point that it basically doesn't happen. So these conditions are good for SN2 reactions, but this substrate doesn't work with SN2 reactions, so this isn't going to happen. But what can we do to put a chlorine in the place of that the hydroxyl group? There are some other conditions we can use to do the same substitution, but through an SN1 mechanism. Hydrochloric acid and some ether solvent, or you could clearly just use hydrochloric acid probably. That's not prettiest, right? So hydrochloric acid, it's an acid. It's a weak nucleophile that favors SN1. So this will do an SN1 mechanism, which does work perfectly fine. There's nothing wrong with SN1 on a secondary position. And if anything, this position here might allow for an alkyl shift, but we're not going to worry about that right now. So this works. And then we don't show the dash in the product because it doesn't, SN1 leads to a loss of stereochemistry. Okay. instead of drawing this 4 times, I'm going to use, because it's the same substrate every time, I'm just going to put all of the charges in the same picture. Okay, so this question is just ranking the stability of these carbocations. Just a bit of review. So when we're ranking the stability of cations, what is the trend for stability? So like the more substituted it is, does that mean it's more or less stable? By that I mean like a secondary is more substituted than a primary. Is secondary more or less stable than a primary cation? Okay, it would be more stable. So more substituted cations are more stable. So the general trend is tertiary is more stable than secondary, which is more stable than primary, which is more stable than a methyl cation. Okay. So we can look at these cations and determine what they are. This one on the top is primary because it's only bonded to one other carbon. This one right here is bonded to 2 other carbons, so it's tertiary. This is bonded to 2 carbons, so it's secondary. I'm going to erase this. And then this cation here is bonded to 2 carbons, so it's secondary. Do these 2 secondary cations have the same stability? Or is there a difference between them? Yes, this one on the right is allylic because it is right next to a double bond. So is this more or less stable than the other one? They're approximately the same. So you're saying that this secondary cation is basically the same stability as this secondary cation? Is that in his notes? That just, I mean, I believe that he said that. That's not how I learned it. I'm gonna double check really quickly. Was that today? Oh, he hasn't annotated today's yet. If that's the case, then go with what he told you. It just, even if they're approximately equal, I'm gonna go ahead and say that the allylic one is at least a little bit more stable than the non-allylic one because there is resonance here and there's not resonance with a non-allylic cation. Are you sure? I'm gonna, because I'm pretty sure I know what graphic he used. Sorry. You're talking. Okay, I know why he did that. What? I'm assuming you have the graphic or like some notes that he had along with it, and I believe he. Crap. I believe he was drawing primary cations for this. So like probably something like this. This is a primary allylic cation. So a primary allylic cation has roughly the same stability as a secondary cation, but it's more stable than a primary cation that's not allylic. I'm pretty sure that's what he was trying to say, but he might not have emphasized that, because I do remember seeing he drew a primary cation and then he looked at this, and that's why it's shown this way. So probably should have said primary allylic and primary benzylic and not just allylic, because that's a bit misleading. Because if we compare this secondary cation to this secondary cation that's allylic, you know that there is resonance because it's next to the double bond, and resonance makes things more stable. So this will be okay. Well, I'm glad I cleared it up at least, because I was a little off put by when I saw it, but I was assuming he covered that distinction. I guess he didn't, but now you know. So if you're comparing two things that have the same substitution, but one is allylic, that's more stable than the other. But like, because we're saying that a primary allylic is roughly the same stability as a secondary, then a secondary allylic is roughly the same stability as a tertiary. So we could theoretically say like both these two are both one, like they're the most stable. I feel like the allylic one would be a bit more stable than the tertiary one, but it's basically impossible to tell. That was the main point of this graphic. So you can kind of consider a secondary allylic as a tertiary cation if you want, I guess. And then a primary allylic is a secondary cation in terms of this graphic. I don't know how else to put it. If it's up to interpretation, he probably wouldn't mark you down. Okay, but after that, secondary is second most stable, and then crap, primary is least stable. Okay, that took longer than I wanted, but I'm glad it cleared up that confusion. I rotated this a bit, but it's going to be the same molecule, just from a slightly different perspective. Oh, that's not where that goes then. I need to move this. Okay, so these are all alkyl chlorides that could act as leaving groups. And this question is asking to rank the reactivity of these different alkyl halides in an SN1 reaction. So how can we go about doing that? What can we consider to figure that out? Yeah, carbocation stability, because SN1 mechanism involves a carbocation intermediate. So I put that chlorine in the wrong spot. I knew something was wrong. Okay. So this is basically the same question as number 4. It's just put in a different context. But if you recognize that things for SN1 reactions follow the same trends, like in terms of speed as carbocation stability, then you'd know that it's the same question. So I'm just gonna label the substitution on all of these. Again, we have two different secondary positions, but one of them is right next to a double bond, while the other one is not right next to a double bond. So it's going to follow the same exact trend as we just saw in the last problem. And I'm not going to belabor that. If there are any questions about this, ask, but I'm assuming you guys got number 4, and this is, again, the same idea. I know I have a lot of review on this worksheet, and that's because you're gonna get into elimination reactions, and like these last two have to do with elimination, which you'll see on Thursday. Okay, what is the trend for alkene stability? So more substituents, the more substituents it has, does that mean it's more or less stable? More stable, that is correct. It's the same trend as carbocations and radicals. More substituents means more stable. So I'll go from left to right. This one on the left, the double bond has 2 substituents, so it's di-substituted. The next one has 3 substituents, so it's tri-substituted. This one in the middle has 1, 2, 3, 4. So it's tetra-substituted. And then this one on the right only has 1, so it's mono-substituted. If there are any questions on how I figured out the substitution of all of these, I can try to explain in more detail, but hopefully you all can see that. So if more substituents means more stable, then this tetra-substituted is the most stable, followed by the tri-substituted, and then di and mono, and I won't belabor that because that just is the trend. Okay. I don't know if he's gonna cover this. I'm assuming since he pushed the exam back, it's gonna come up. I mean, not just a chair flip, but like you should recall this because it might come up with elimination reactions. Okay, so one part of the question is asking to label the substituents as axial or equatorial. What is this chlorine here? Is it axial or equatorial? Yes, it's axial. What about this methyl group here? Yep. This bromine. And then this methyl group here is equatorial. So something is axial if it's straight up or down. And then it's equatorial if it's more in the plane of the molecule. I don't know how else to put that. But I think the way I've always done it is I identified like what direction the axial is. And it alternates straight up and straight down. So like those are all the axial positions. And since I did this, I'm gonna do that. Those are just the axial hydrogens. They're all alternating up and down at each carbon. And then the equatorial is just kind of going off to the side in the other direction, up or down, depending on what it is. And again, like this will likely come up in the context of elimination reactions. So it's good to understand like when something's axial versus equatorial. And you should be able to do a ring flip for these chairs. Okay, so when I do a ring flip, I guess I'm gonna number these carbons up to 4, or I guess 5. Is the chlorine here gonna be on carbon 1 still when I do the ring flip? Or is it gonna go somewhere else? I know this has been a while, so it's okay. Well, okay, if we numbered it, it would still be 1, but like when you do when you do a ring flip, you basically move all of the substituents clockwise. Yeah, okay, so I understand now. You got it. So yeah, it's gonna go from being in the top right to being on this bottom right position. And is it going to be axial or equatorial now? Yep. So you can look at it 2 ways. It's either flipping from axial to equatorial, or you can look at it as it was pointing up when we started, and it's still pointing up here because this is the axial position. The equatorial is pointing up relative to the axial. So that is what Jared pointed out, and that is a very good way of looking at it. It stays up. Okay, so we already pointed out this is equatorial. There was a methyl group here. It's going to move to this position here. Is it going to be axial or equatorial? Yep, so it's going to point down. I like that little thing at the end. So it moved 1 over and it stayed down, so it's axial. And then the things that were on carbon 4 are moving up here. Is the bromine going to be axial or equatorial? So it's axial here, it's going to be equatorial there, yeah. And then the methyl group is on the other position. So if this comes up, you've seen it again, and it's just good to review because it'll come up on the final anyway. But yeah, that is all I have for today. I hope this mostly review of last week helped. I'll shut off the recording.